Okay. So yeah, hi. Yeah, so we're going to be doing the Fermat's little theorem and Euler's theorem today. And so first of all, I would want to like say to not move everything around like some people are doing right now, because it's very distracting, and it disrupts the class. So yeah. Okay, so we're going to start now. Uh, and I hope everybody who wants to be here is here. Hmm, wait, let me fix this. Let me like change this. Okay, anyways. Now we're going to start. Um, yeah, as I said, we're going to be going over Fermat's little theorem as well as Euler's theorem, and then we'll like do some problems. And so first, in order to prove Fermat's little theorem, we're going to go over Bezout's identity, which is needed. And so Bezout's identity says that for any non-zero integers a and b, you can choose. I mean, you can find such a x and a y in the integers. Well, and x and y are not necessarily positive, such that ax plus by equals 1. Um, and so I think I meant to write for two non-zero um relatively prime integers, because if a and b are not relatively prime, then this can't happen. And the generalization is that for if GCD of a and b is equal to d, then you can find integers x and y such that ax plus by equals d. Before that, today it's not very important. Anyways, so yeah. For the proof, you can use the Euclidean algorithm for the GCD, and yeah, you can search that up, but I won't be covering that today, or else we're gonna take way too long. Okay, so for the next one, we're going to cover the existence of modular inverses. So this theorem says that for any positive integer of n greater than or equal to 2, and there is a positive integer a, which is at least 1, and these two are relatively prime, or their GCD is 1, then mod n, uh, there exists a unique residue b, such that a times b equals 1. Basically, what this says is that for any mod n, we can, and given a residue a. And so like if you don't know, a residue means like a certain remainder. So like for example, if there's mod n, then you have n minus 1 residues. And so for this, given a residue a, there's a unique a unique residue corresponding to this value equivalent to b, which is defined to be a times b is congruent to uh 1 mod n. And so it's like that's how like the inverse is defined. And um this theorem says that if n and a are relatively prime, then there exists a unique residue that satisfies this property. Okay. And so to prove this, we can apply Bezout's identity. So we can have Bezout's identity on n and a because we have this condition. So we have nx plus ay equals 1, and then there's unique it's not unique. There exists integers x and y, such as this is true. And to change it into this form, we can let b equal y and let k equal negative x. And so AB equals 1, or is congruent, we should do congruent to like mod n, is congruent to 1 plus kn mod n. And so what we can do is we can cancel out this because it's divisible by k, and we can find there exists such a thing. And then you can also show that it's unique. But we're not gonna do that. But wait, can you see that? Oh, sorry if you couldn't see, but yeah. So that's how you prove this theorem. And with these two theorems, we can finally move on to the first extremely important um we can first we can now go over the first extremely important and like major theorem we're going over today, called the Fermat's Little theorem. And so Fermat's Little theorem is this theorem that says if there's a prime number p and there's a number n such that p does not divide n, well, this implies that their GCD is 1, right? Since p is a prime. Then n to the p minus 1 is congruent to 1 mod p. And then the second part is a generalization that isn't really Fermat's little theorem, but it's close. So anyways, to start with this, we can do like a very standard proof, right? So we start with a set of residues 1, 2, 3, all the way to p minus 1. And so what we're gonna do is we're gonna multiply this set of residues by n to get this other set. And so what we did is that we multiplied each element by n. But remember, we're doing all of this under a mod p scenario. So, by the existence of modular inverses and the fact that multiplication is commutative, um, we can like see that these two sets um are equal. I mean, there's like a one-to-one mapping at least, and we can show that they're equal. And so yeah, so like these two sets are like congruent mod p. And uh s so we can show like these are equal, and then we're going to take the product of all these terms. So for the first part, we get like p minus 1 factorial. For the second, we get like n to the p minus 1th power with p minus 1 factorial. And these two are congruent because we multiply the same residues together, so their product should be the same, or at least congruent. And so then we can cancel out p minus 1 factorial since it's not congruent to 0, and you get n to the p minus 1 is congruent to 1 mod p. And so to prove the more general form, as long as n is not divisible by p, we can multiply by n on both sides to get np is congruent to n mod p. And if it is divisible by p, we can like directly calculate it. So np will be congruent to 0, which is congruent to n mod p. So this is the second part. We proved the second part. So yeah, so this is how you do the Fermat's Little theorem. And so for this theorem, the major restriction is that it has to be a prime number p. And so like that's what the Euler theorem is going to like is going to cover. But we'll do that later. So yeah. And then after this, like we can talk about like the converse, but like unlike most theorems that have a converse, this one is not true. It's like most numbers won't satisfy most numbers will satisfy the converse, but not all numbers that satisfy the converse. Um, so the converse is not generally true. In fact, there's a list of Carmichael numbers starting with 561 um that do not satisfy the converse of FLT. And basically it's not true, so you must be careful. So if you find a number and it's not congruent to it's not congruent to 1 if you take it to the p minus 1th factorial, I mean p minus 1th power, it doesn't necessarily mean that p is um prime. So you have to be careful about that. And then we will cover this um uh then we will cover the Chinese remainder theorem. This is commonly used with the um Fermat's Little theorem and Euler's theorem. And so basically what it says, so that if we have two different things, like two different modulo m and n, and there are like relatively prime, so their GCD is 1, then if we have residues mod m and n, such as like if we have like a number z, or like if we have like a residue x mod n m and y mod n, then we can find a unique residue z mod m times n, such that z is congruent to x mod m and z is congruent to y mod n. And so yes, this is what the theorem says. So we can use this when the Euler theorem doesn't, or I mean the Euler theorem doesn't, conditions are not satisfied, and we'll see that in use in the final problem in today's lesson. So like, yeah, but like the Euler theorem is coming up. Anyways, this is like an important theorem you can use in case you have to split up the modulo into like the smaller ones. And with the Euler theorem and Fermat's Little theorem, this is very useful. There's also a generalized theorem where you can have multiple yeah, you can have like much more residues. Like if I have like A mod B and like C mod D, and these are all pairwise relatively prime, then we can find a Z that is congruent to like A mod B. Z is congruent to C mod D. But we don't use that. We're not gonna use that today, and we don't use that on the homework too. So, in case you want to know, you can search up the Chinese remainder theorem. And you can search up the proof. We're not covering the proof because it's also gonna make this lesson too long. And so at this point, is there any questions about like the Fermat's Little theorem and the Chinese remainder theorem? Okay, so I'm assuming that's a no. And then next, before we do the uh before we do the before we do the Euler theorem, we're gonna first have to cover an important part before the Euler theorem, or that we need to know before the Euler theorem, called the Euler's totient function. Okay, so The Euler-Toshin function is defined as the number of positive integers less than n and relatively prime to n. Okay, and we denote it to be denote it to be phi of n. And just to let you know, phi is a Greek letter and it's written both this way and this way. And so if you see this way, like, don't be confused. This is the same thing as writing it this way. Like the same thing basically. Like in different fonts, they look different, but that's like not the point. So yeah, this is a very nice function. And so if you don't look at the formula, like if you somehow like don't see the formula here, I should have done this earlier. If you like don't see the formula, right? There's no good formula for it. Right. So it's like a lot of functions are defined this way, right? There's like not a good way to calculate it, but like we'll calculate our other we'll still calculate it, right? We'll try and like um let's see like 20. So if you write out the numbers from 1 to 20, and then you cross out the numbers that are not relatively prime. So like 1 is relatively prime, 2 and 20 has a GCD of 2, 3 is relatively prime, 4 has a GCD of 2, 5 has a GCD of 5, 6 has a GCD of 2, 8 has a GCD of 2, 10 has a GCD of 10, 12 has a GCD of 2, has a GCD of 4, I think. Oops. 14 has a GCD of 2, 16 has a GCD of 4, 18 has a GCD of 2, uh, 15 has a GCD of 5, and 20 has a GCD of 20. So if we cross it out, we have 1, 3, 7, 9, 11, 13, 17, and 19. And if you count the numbers, there are 8 numbers. So we successfully calculated phi of 20 to be equal to 8. Okay, so if you already know Euler's theorem, or like you're like thinking about this, right? If you want to calculate like phi of like 100, which is equal to 40, um, then it's gonna take a very long time because you don't want to list every single thing out. Um, and so yeah, so we have a formula that's like we can like derive it actually instead of like looking at that formula because like that's like boring. Like if you don't know that formula, this is how you like find it. Anyways, so like we're gonna like try to find the formula now. There's a question. Is it like phi m times phi n equals phi m n? That's a property, not a formula. It's not the formula that we're talking about. Although in that case, m and n do have to be relatively prime. Yeah, that's multiplicity, right? You can like search it up like multiplicative functions. I don't know how to prove that. I just realized. Like, I mean, it's obvious, but now that I think of it, it's kind of obvious. And I have the formula. But whatever. Okay, we're first gonna find the formula first. And so in this case, where you're counting by factors, it's nice to have a prime factorization. And by the fundamental theorem of arithmetic, we can like factor every single number into a unique prime factorization. So we're gonna borrow that fact and like list out the prime factors of our number n. Okay, so our number n will have prime factors p1, p2, p3, all the way to pk. Okay, so now we're going to use complementary counting and calculate our number as n minus the number of numbers from 1 to n such that they have a non-zero GCD. I'm gonna with like n. So like I'm going to like write it like this, right? So now we have this like complementary counting form. And this is slightly easier to count since instead of counting like gaps, we're now counting like things that are we like colored in. And so like or like crossed out in like the last case. And so for this, we use the common counting method called PIE or the principle of inclusion and exclusion, which means you basically count well, like we're splitting it over the factor, like the prime factors, right? So you first have to like count the number of them that are like divisible by like P1 and like add that to the number that are divisible by P2 and then add that to the number that is divisible by P3 and so on until you get PK. But then like you have to subtract the ones that are divisible by two of them and then add back the ones that are divisible by three of them and so on. And so that's like the that's how like PIE works. I also recommend you find out what that means and how that works. It's very useful, especially in counting. But this feels like a counting problem anyways, not number theory. Anyways, so like we do like n minus 1 over p1 plus 1 over p2 plus 1 over p3 dot to 1 over uh I mean n, right? N over pk. And in order to avoid floors, we just uh avoid we avoid floors by noting that n is divisible by each of these, so all of these are integers. And so we need to subtract n over p1, p2, and then n over p1, p3, and so on until we get like n over pk minus 1 pk, what they call them. And then we add back the three ones to minus the ones that have four. Then we add back the ones that have five, and we keep going until we get like plus or minus n over p1, p2, all the way to pk. And so this is the end of our like PIE thing. And then so the rest is like algebra. And then you algebra it out and you factor it. You can factor out and you can like take away the parentheses, factor everything out. And then what you have is this formula of n times 1 minus 1 over p1 times 1 minus 1 over p2 plus times 1 minus 1 over p3 and so on. And so this is the uh, main like thing. This is like the main formula we're going to like be like using and like mostly well known. Somebody asked, will we be covering orders today? Yes. Yes, if you're wondering, yes. Wait, isn't there something like E1 plus 1 times E2 plus 1 for counting factors? Oh, we're not counting factors. Like, for example, 8 is not a factor of 20. It doesn't, 20, 8 isn't divisible by 20. But GCD 8 and 20 is equal to like 4. So like you can't include that, but it's not a factor. Okay. So, okay. I hope that question's answered. Um, there seems to be a lot of questions. Feel free to ask any questions just in general. So I'm just gonna check right now. Is there any questions? Okay. I'll take that as a no. And so we did spend quite a lot of time on this one. And if you want to know, yeah, that's what I wrote here. So it is actually the formula. I'm not tricking you. So if you search it up, that's the formula you get. There is another one, but that one's like not useful. Like according to my experience, I don't use that one. And then so we're gonna move on to the next part. Um, Somebody asked what's the other one, and I think the other one is like you multiply like the prime factorization of n into the like parentheses. So like you get sort of a slightly different version. I mean, it's the same formula, but I mean, it's the same formula, but it's like written different, like in case you need it. But I don't think anybody would need it. Okay, so we're going to talk about this property called multiplicity. And so multiplicity is a pretty advanced number theory function thing. And it states if a function f is multiplicative, like if f is multiplicative, then um you can get fa times fb equals f times ab if GCD of a and b equals to 1. And there's actually quite a lot of things here. And there's quite a lot um of like properties of this. There's a question that says if n equals this, then does phi of n equal phi of the product of the prime factors? No, it does not. So if you're wondering, no, it does not. But although if you do multiply it by the rest of the remaining parts, yeah. And so in order to uh prove this property, and another note on the multiplicative part, yeah, we need this on the homework. But like it's for like the challenge question. It's quite a big area of mathematics. You can like search it out. Or like a big area of number theory. Or like multiplicative functions. Yeah, it's like a number theory thing. But anyways, we're gonna prove it's multiplicative. And although there are many other ways, which I could mention, I don't want to mention actually. It's so painful. Okay, so in order to prove it's multiplicative, we head back to the formula. And so for the formula, there are two parts. There's the m part and there's like the m or n part. And then there's like the 1 minus like fact, the, the prime factors part. Oops. And so like, so it looks something like this. Oh, oops. Like something like this. It's like, anyways, it's like something like this, right? And so we're assuming A and B are relatively prime. I mean, M and N are relatively prime, right? So all these prime factors will be different. And so if we multiply it up into Mn times a long list of 1 minus 1 of our prime factors, then all the terms will be different in the second part, and therefore uh like everything will work out and you'll end up with a formula with M and N. So here this will be M and N instead. And so like yeah. Uh so yeah, that's how you prove the multiplicative property. And you can use this to do like some proofs too, including like you can like prove this in another way, like sort of prove it for the prime numbers and then prove it for everything else. So yeah. So next we're gonna cover Euler's theorem. And I see somebody put this here and somebody put this here. So I think Yichen will be doing this first. So
Oh, okay. So Euler's theorem is a more general form of FLT. So you might notice that like for a prime p, like phi p is just like p minus one. So like it's a more generalized form for FLT. So the proof for it, I'll be using something called a reduced residue system. Basically, a reduced residue system. By the what just happened? Reduced. I'm gonna just click on something. So a reduced residue system is basically like the set of all like remainders a1 a2 ak, such that like each one of these remainders is like relatively prime with our number n that we are doing mod here. So basically the proof for Euler's theorem, we can let this right here be a reduced residue system mod n. So here, and this totally has k equals phi in terms, right? It's because that's just like the definition of phi. So then if we like let a be an integer such that GCD a and n is 1, then after we multiply a to every single number or like remainder in this system right here, then we get something like a1 a2 a n. And because this above is a reduced residue system, this thing right here is still a reduced residue system. And that means that they must have the same remainder when multiplied together modulo p. So this means that we would have a1, a2, a3, ak. This product is equal is or is congruent to this is a k by the way. This is a times a to the kth power and then A1, A2, AK. Now these are all relatively prime to n, like these A1, A2, A And then because we proved earlier that each of like these numbers must have an inverse, we can like multiply these each by A1 -1, A2 -1, AK -1 on both sides. It's messy, okay. And then after we multiply this, these all become 1. So we just get 1 equals a to the k mod n. And above here, we define that k is by n. So this just proves Euler's theorem. And again, this is a generalized form for FLT. Any questions for this proof? I assume not. So then we'll be going to our next slide, which is this Olympia number 3 lemma. Now, this lemma will be useful for some examples and potentially problems you might see in the AIME or JMO if you're going to take it. So this lemma, I won't be really covering the proof because the proof is really like not pretty tedious. It's just like reapplying Euclidean algorithm, which is like the way to like determine their GCD. So like you have this right here, which is just say GCD a to the n minus 1, and a to the n minus 1 equals a to the GCD n minus 1. So this will be useful in a problem we'll do later. So yeah. Now next slide. So now order is something else that is really important for number 3, especially like recently in the AIME, there's been more order questions than like FLT Eulers. So like order is like it's like more advanced, but also like more important. So basically, the definition of order is like the minimum, the minimum k, such that n to the k equals 1 mod m. And this must always be a factor of phi to the m. Any questions about this before I give the proof? Okay, I assume no questions. So the proof that I have is that if we can prove this by contradiction, right? So like let k be the order, but k is not a factor of phi of m, then this means that here we have like again n to the k. So I haven't like this. So n we have n to the k equals 1 mod m here. And this is the smallest integer which satisfies these conditions. So that means that here, if we let phi m be equal to k times d, plus r, then this means that, well, n to the phi of m here, which this should be congruent to n to the k times d plus r. No, the plus r is like above here, by the way, just saying. So, erase this. So over here, this is just congruent to n to the r. Now here, because we assume that k is the order, this means that this r is less than k because r takes the remainder when we divide phi m by k. But this nr cannot be equal to 1 because or else this contradicts with our statement here. So basically, this is saying that n to the phi of m is not congruent to 1 mod m. But this is not allowed because that's just literally saying that Euler's theorem is not true, but it is true. So this is just why the this order k must be a factor of phi to m. So, yeah. So that's why this holds. Any questions for this? What's this? I'll be going to our next. No. So that's it for our content. So now we'll be going over some examples where like these theorems can be applied. So our first example is this one. I'll give you guys half a minute to think about it and like we'll go over it. Okay, so does anyone have any ideas for this first question right here? Okay, I assume not. So I'll just go over this. So first I'll be covering this factorization. So what does, oh, that's just like divisible by. That means like that's a factor of the, this basically is trying basically prove that like 773 is, oh my God, what is this happening, bro? Okay, I assume no one has ideas for this then. So I'll just go over this. So basically here, I'll first cover this factorization. So for an expression of the form a to the kth power minus 1, we can factorize this as a to the k, a minus 1 times a to the k minus 1 plus a to the k minus 2, and then plus so on, all the way to 1. This you may recognize as a formula for the sum of geometric series, which is very similar, or maybe perhaps even the same. So after this, we can express this thing as 4 times 10 to the 771 plus 10 to the 770 plus so on all the way to 10 to the 0. So here we can rewrite this as 4 times 10 to the 772 minus 1 over 10 minus 1. Now, clearly here, this 4 is irrelevant. Also, I will just point out that this 773 is like prime, I think. So this 4, these are all irrelevant. So here, after you know about like FLT that 10 to the 772th power equals 1 mod 773 just by FLT. So this 773 is a factor of 10 to the 772 minus 1. And this just completes this proof. Any questions for this? I assume not. So then we'll do the second example, which is I think much harder. I'll give you guys. Okay, there's actually a question here. So someone asked me how do I get the 10 here? Can I please specify what you meant? Oh, so this 10 right here? Well, just like for example 40, right? There's a 40 here, right? This is 40 just 4 times 10 to the power of 1. Like yeah, similarly for everything else. Like it's this formula right here that I just like wrote down. I hope that clears it up. So now we'll be moving on to question 2 for real now. So this question, wait, so this is a lot harder, so I'll give you guys 3 minutes for this question. And if you have any ideas, please send it to me. Okay. I have gotten several ideas from people. So there's 2 main ideas that I've got so far. So one idea is turning this into a geometric series that we can like use the formula from like before to do, which I didn't think of, but it's actually a great solution also. But the solution that I planned to do was just like you do CRT here and then like just use Euler's theorem here. Also like the reduced residue. So to solve this question, we could first factor 1,000 into 8 and 125. So notice that 8 is a power of 2. So that means that like we have to like, do a separate case because like for n is greater than or equal to 3, then what's gonna happen here is that 2 to the n will be a multiple of 8. But however, for n equals 0, 1, and 2, we will have 1, 2, and 4 respectively. So we'll first keep this aside because for the rest of the numbers there won't be like such special cases. So now we just consider them mod 125. So to do this, we can first figure out that 2 to the negative 50th power mod 125. No, wait, what am I doing? No. 2 to the 50th power, sorry, not negative 50th power. This mod 125 is equal to negative 1. So we can similarly show something for 2 to 20th power. What? Please don't draw stuff. So once we know these, this just confirms that the order of two. What? This just confirms that the order of two. Wait, what? Order of two mod 125. This is just gonna be what 100. So this means that if we just like consider two to the k mod 125. For 0 less than k, less than 100, no, less than 99. So each of these integers k here will yield a different remainder mod 125. And this is useful because this means that basically it's just gonna be like 1, 2, 3, 4, 6, 7, 8, 9, etc. Now, if we also combine this with the 0 mod 8 condition, then these will basically just be like 8, 16, 24, 32. Skip 40 because it must be relatively prime to 125. So to 48 immediately, like yeah, so on. Now this ends up 992. So if you look closely at these, you may notice that some things here add up to 2000. And also this is AIME. So like it just asks for mod 1000. So like here, these two cancel out. Like if you just like write down the whole thing, 984 here, everything here cancels out. So that means that this whole thing is just canceling out. It's 0 mod 1000. So then it only leaves these three, which we separated out. This is just 0, 0, 7 when you add them up, which is indeed our final answer. So any questions for this? Oh, I should also mention the geometric series method. So the geometric series method, you can also do something similar here. I'll just say I won't like actually do it though. So like you of course also set aside like these. Like you can do something similar like 2 to the 0th power plus 2 to the 1 plus. Now this is like equal to this is just equal to like what 2 to the 100th minus 1, and this is 0 mod 125. So like here also cancels out similar thing. Just mention it here. It's like people suggested it. So any questions for this? Okay, I assume not. So now because apparently Zoom whiteboards can't be too big, we have to change a whiteboard because like we can't add more pages. So I'll do that real quick. Thank you, Edward, for that. So now we'll be going over perhaps the hardest question that we'll be covering for this. This is a recent AIME question and it's really difficult. 2024, last year, AIME 1 question 13. Now this combines, I'd say, orders, FLT, and also a formula called lifting the exponent, which I'll mention later, or I'll just post it right now. So I'll give you guys 5 minutes to work on it for a sec. And if you can't solve it, don't panic because this is like really hard. And by the way, here is LTE right here, so I'll just say, oh my God, I can't remember right now. So VP is defined as largest power of. That's just different real quick. So like I'll just tell you guys.
There's the typo in the question if Yichen could zoom in for us. It's like right here. Um, there's supposed to be a let, I think. So, yeah, in case you're wondering. Wait, if you're also wondering, it's a repeated twice. So like, yeah, ignore all of this. I just realized.
This problem is not repeated twice. No,
It,
this problem is not repeated twice. Just read it carefully, please.
it literally is.
It's not.
If you're wondering, you can like look at the
Oh
AOPM.
wait, it actually is. Never mind. Okay, I'm done.
Exactly.
So not sure how this happened.
Yeah, so you can like
Yeah,
ignore
yeah.
that.
Cross this out. Cross this out.
I would remind you to like maybe start drawing random things. Or is that each end? I don't know. I can't tell.
I think that's about time. So this question is definitely harder. So some ideas I've gotten were, well, first of all, we can at least note that like here P is odd, right? Because like you can't really have like even P here. Yeah, so someone said P is odd, which is correct. So we first know that P here is odd. And someone else also mentioned that we can like use n to the fourth power plus 1 equals 0 mod p first, because like p is much easier to deal with than p squared. And yeah, this is what the solution involves. So I'll just go over it now. So once you get this thing, I'll do it down here. So once you get this thing, this also means that n to the power of 8, yeah, that's the order basically, because 4 doesn't work. So n to the power of 8 equals 1 mod p. This means that 8 is the order. So that means that 8 is a factor of p minus 1. So here, we can basically deduce that this p should be 17, because here it's just like it's the least prime number, so it should be 17 here. So now here we can just like plug this p back in here. So we want v7. I'll use LT here, right here, as you guys can see. So here we want v17 of n to the fourth power plus 1 equals 2. So we can write this as v17 times wait, let me just check this again. Yeah, v17 times, wait, not this. So after we see here, if we use LT, we can find out that v17 of 2 to the 68 plus 1 here works, because if we let n be 2 to the 17 here, then this satisfies all of these conditions, because well, x plus y, that's just 2 to the fourth plus 1. That's what we need. And then for the exponent, which is n this n, this must be a multiple of 17, so it should be 68. So this is equal to 2. And after we get this, we can just start testing out. So we know that 2 to the power of 17 works. Right. So if we know 2 to the power of 17 works, then all of the odd powers of this should also work, but even powers will not work. So basically here, if 2 to the 17 works, 2 to the power of 34 does not work, but 2 to the power of 51 will work. Then like 2 to the power of 85, and then 2 to the power of 119. So these are just all of um the potential answers for this question. But this question asks for the least positive integer m, and these are all, of course, not gonna be the answers. So you have to then take these all mod 289. Now this is a really tedious process that I won't be going over, but after you like check all these things mod 289, you should get that the final answer is 2 to the 51, which is 110. So like, and just like checking these. Okay. Um, does anyone have any questions for this? Oh. Okay, I assume not. So then we'll be doing the next question, which I'll leave to Edward.
Okay. Uh, so wait. Okay. Okay. So here. Then we have another question. Um, and so this is a question from the PUMAC, which is Princeton University mathematics competition. That's what it stands for. Okay, so we can start this. This is the question I was referring to at the start when I said we're gonna be using CRT a lot. And so this question is basically using CRT, FLT, and Euler's theorem. And so before I spoil everything, I'm gonna let everybody like try it out for like 5 minutes. It's not like extremely hard, but it does take some time. If you have any ideas, please send it to me or Yichen. But I would prefer if you send it to me because I'm presenting. I would like to remind everyone that you cannot use Euler's theorem if the base is not relatively prime with a mod. So like in this case, 2008 is not relatively prime with 1000, so you cannot directly apply Euler's theorem here. If you have any questions, it'd be great if you private message me. Okay, so it looks like 5 minutes are up. A lot of people got very close and like actually correct thoughts. So what you do like they suggested using CRT, which is Chinese remainder theorem, and then applying Euler's theorem and FLT to like work your way. And so there was a question asking, do I do from the bottom or the top? Generally, it's smarter to do from the bottom, since if you're doing from the top, you don't know what mod to consider, and it's like very far away. You're not calculating it. You're doing a mod. If you're calculating it, you do like top to bottom. But if we're doing mod, the strategy is to go from bottom to top. Actually, this question does not take very long, if you're wondering. It's not like it doesn't take like horribly long. You can like solve in like 10-ish minutes, but we don't have like that much time. So we're going to like finish this first up. If you have any questions though, you can ask. Okay, so to start, we have to use Chinese remainder theorem first because to calculate to this mod of 1000, we first have to get rid of the 2 and 1000. So we're gonna split into mod A and mod 125. I think a lot of people got to this step. So in general, in these type of problems, if you cannot calculate it uh directly, you do like a CRT first, and then you take the um Euler's theorem on the other half, or the FLT. So like that's like the general strategy. Um, and otherwise you think about it if that doesn't work. So anyways, yes, it's 0 mod 8 because 2008 is congruent to 0 mod 2, and we're taking it to like this like extremely large power, so it's 0 mod 8. And so we need to find out what it is mod 125. And so to use that, we first can like take the base mod 125. So it's like 8 to the 2007 to the 2006 all the way to 2 1. And this is like mod 126, I mean 125. And so we're basically 8 to the 100, which is 8 to the totient 125. That's congruent to 1 mod 125. And so in this type of problem, the general spirit is that you take like the exponent mod the totient. So now what I'm basically doing is I'm gonna take the exponent 2007, 2006, 2005, etc. to 1 mod 100. And then I can like put this back here and substitute that back. Is 40 uh is it 48 mod 125? Assuming the answer, I'll tell you. Uh so for this one, we can apply the directly or apply modular properties again. So we put like 7 to the power of 2006 to 1 mod 100. And we can apply this again. And so what we're going to do is we're going to calculate 2006 to 2005 all the way to 2 1 mod 40. And after that, we're going to substitute it back here. And so at this step, um, so how do you arrive at 100? Again, um, it's totient 125, which you can use the formula. I don't have the formula here, but yeah, I hope you know the formula by now. If you not like, okay. So, so now we're going to do this again, but realize that you can't use Euler's theorem. It's a common mistake. You can't just like use Euler's theorem here, right? 2006 and 40 share a common factor of like 2. So now we're gonna use Chinese remainder theorem again and do this by splitting this into mod 5 and mod 8. Mod 8, it's obviously 0, and mod 5, it's obviously 1. So mod 40, it's obviously 16, and we can substitute it back here. And now we're going back, right? There is a couple questions. Uh, but isn't it orders of 7 mod 100? So, but isn't order of 7 mod 100 the order so I think the question is asking but isn't the order of 7 mod 104, so you only need to do it mod 4. I'm assuming you don't know what the order is though. So yeah, it's true. It is the order is 4. So you do that, that also works. But I didn't do it that way. I think it still works because at this point you're taking a 7th to the 16th power, which you'll realize is 4 pretty quickly. So if you don't know it's 4 yet, you can like do this. So the 7th to the 16th power is equal to 49th. It's congruent to 49th to the 8th power, which is congruent to 50 minus 1 squared, and then to the 4th power, which you can expand to be 2500 minus 100 plus 1 to the 4th. And at this point, you realize this is like 1 to the 4th. So that's 1 mod 100. Oh, okay. So then we can like go back here. So here we got 1. So we can substitute it back here. And so moving all the way back, we find we were just doing 8 to the 1 mod 125. And that's 8, right? And so our answer is 8 at the end. The last 3 digits are 8. So, is there any questions about this process? Okay, I'll take this as a no. I'm just gonna say that this type of question or this type of like process is very common in the like AMCs. So I gave you like some corresponding like questions on the homework to practice it. It looks much simpler because there isn't that many layers, but you're basically doing the same thing, like sort of. So yeah, you're just like applying that, if you can see. And so we're gonna go back to the last question. And I think each hand is like gonna be doing this question.
Okay, so this question, well, looking at it, will give you like a nightmare. I guess it's like it looks so ugly, but I'll give you guys like I guess 3 minutes to like work on it yourselves, and like just keep in mind that this looks bad, but like it's not that bad when you actually try to simplify it. Oh, also just saying, because I forgot to mention this, but like this problem is PMAC number 3B3 2022. Okay. Hmm. I guess now I'll go over this question. So at first glance, this question looks like really almost looks impossible to do. But once you like notice like how this is, you can just simplify this and like this, it becomes a lot simpler. So I think first of all, like cross out these like mod p, right? Just cross these out, like because like now we just have 20 p squared plus p plus 2 plus 4 times p. No, wait, no. 4 times 22, sorry, p squared minus p plus 1. Wait, I'm gonna replace some chat messages right now. So from here on, we can like further use FLT to like simplify this thing even further. So like after we use FLT here, then we get this is gonna be 20 to the fourth power because like you have p squared plus p minus 2 is like um yeah, and this is gonna be 4 times 22 to the I believe also fourth power because like um p minus 1 is like division by p minus p. So after you do this, you can like try to factor this. So like if we try factoring this, we can like use I believe like the Sophie Germain identity, which like let us factor this as like 2 to the fourth power times 10 to the fourth power plus 4 times 11 to the fourth power. Now we can just further factor this by like completing this square like into 2 to the fourth power 10 squared plus 2 times 11 squared minus 2 times 10 times 11 and then 10 squared plus 2 times 11 squared plus 2 times 10 times 11. Now we can just rewrite this into 2 to the 6th power times 60. 2 to the 6th power times 60, 61, yeah, 61 times 281. So after we get this factorization, it's pretty clear that we just have like 2 plus 61 and 281. Now, I'd also like to give a tip here. So when you see questions like this question right here, which is like really complex, or less complex, like you should always try to like first simplify it first. So like for example here, it's like asking for this thing mod p, right? It's like just cross out the p first because like, that's like irrelevant for like modding for mod ping. So like if you see something really complex, like first try to simplify it before doing anything else. Okay. I think that's about it for our examples. So now since there's still extra time, I'll just quickly show a proof for FLT using combo. So I'll just like guess go somewhere. Here. So so this proof for FLT will be with combo. So um I'll just quickly go over it. So this proof like relies on the main idea that like the number of ways to like do something must be an integer, right? For example, like the number of ways to like color something, like color like something must be an integer. So that's gonna be like how we're gonna prove this. So basically, um, so our combo question here is how many ways can we color a regular polygon where P is a prime with A colors such that we use at least two colors and and colorings are same if they can be rotated into each other. So so here notice that like we can like first draw like this I guess peak right here. It's a horrible drawing, but like yeah. So like there's like points here, 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 etc. So over here, totally like without this constraint of two or more colors, also this rotation constraint, we get that totally we have a to the power of p number of colorings here, right? So after this, then there are totally a colorings where we only use one color. And everything else is like we use at least two colors. So now we just have to like subtract the cases that we overcount. So each coloring can only cycle every one. I guess we can only cycle every one vertex or every p vertices. So that means that here we already subtracted like the ones that cycle every one vertex. So every single coloring that is still remaining, this all the colorings that are remaining all have all p of their rotation still left. For example, like so like I guess a heptagon. I cannot draw one. So like like this heptagon right here, which I'll just like the vertices for. It's like one right here, 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 and one right here. We like every single coloring that's still left that we have not yet subtracted. These are
Can I just like say, somebody's deleting the pages or moving them around in some way. It's really making things like hard for me like right now. So can you like not do that? Also, like I have no idea how to get them back. So like try not to do that.
yeah, please do not delete the pages. It's very distracting. So every single coloring here, like for example, if we color like this one red, this one yellow, yellow, like these are all yellow then. I'm using the wrong pen. Yellow, 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 yellow. Everything else is here is yellow. Then all of these left, like they can't cycle every one color because like or else they're all equal or every single color is equal, right? So that means that we just divide this by p, and this is the total amount of valid colorings with these conditions. So this basically means that p is a factor of a to the power of p minus a. And then this is just Fermat's little theorem because a to the pth power equals a mod p. This is like the generalized form of FLT. So yeah, that's a nice little combo proof for FLT, which involves almost zero number theory. So um now I'll let Edward like show guys like homework and that stuff.
Okay, I'll just like go find out those like other pages that I got later from like the version history or whatever. Anyways, so as I said, these are the first three homework problems. General idea, apply FLT Euler theorem plus CRT for the last one. This is the second two problems. I think Yichen does these, so I don't know how to do them. Oh, wait, I should put guys on me. Anyways, these are the second homework problems. General idea, I think I don't know. I think the idea is you still use like FLT Euler, but they're a little harder. These the last one I think you directly calculate them all or like somehow, and then like expand it, like calculate, and then for the first one you like do this. And then for the challenge questions, I'm gonna give slightly more hints since it's a challenge question or something. And so general idea is that you CRT with Euler's theorem, uh, like CRT with like Euler's theorem, and so like, and then you can like think about it a little, and so like this one will really like uh try to. This one is actually really hard, and so like It's okay if you like don't do it. In general, like the medium ones are like early AIME level easy. Like they shouldn't be too hard. The easy ones are really easy just for like basic mastering of the skills. If you go do the hard ones, it's okay. It's like try, at least try. Okay,
Also,
I think that's it.
please avoid like just search up the answer for this because like you're gonna ruin the problem for you. Like you'll
Yeah,
like just don't like search up answers. It's
we
not
put
good.
the like the we put like the sources there so that if you like um so that like we don't like get into like copyright trouble or something like that, which we don't want to get into. Like don't switch it up. It's not like encouraging you to like switch it up and then look at it like, oh yeah. At least for I suggest like for the easy ones, like you should work on them by yourselves. Really like get used to these. For the medium ones, I don't know, maybe like 10-ish minutes or like 20-ish minutes. Like everybody will take a different amount of time, but it shouldn't be like crazy. But like for the challenge questions, it's gonna take like a long time for something. Don't post answers right now. It's not good. God, thank you for coming. Anyways, bye.
Okay, so thanks for coming and good luck in your future mathematics. Bye.
What is what is this?
Bye. Thanks for teaching.
Bye. Who
Bye.
deleted the? I, I swear though, who
End the
deleted that?
meeting, bro. Just end the meeting before people like delete everything. Just end the meeting, bro. Also,
What is this like for the hard question too? Wait, for the hard
also,
question
this
too?
thing is recorded, so please not spam stuff in the chat.
I'll save the chat so everybody knows.